So it's a pleasure today to have Sabine Jansen from LMU Munich, and she's going to tell us about virial expansions for mixtures, some examples and recent results.
All right. So thank you very much for the opportunity to speak in this seminar series. It's really a great honor. I've been asked to speak about, or suggested to that virial expansions and cluster expansions might be a good topic to speak about. It's always a challenge to take these things up because I'm not sure I will manage to make the talk pain-free, but I try. So let me first say what I plan to do. I will first start with a recap on Meyer and virial expansions. And apologies to the experts because none of it will be new. And I will do this recap not in the setting of polymer partition functions, but in the setup of grand canonical Gibbs measures for particles with pairwise interactions in RD, or to be more precise, in finite volumes subset RD. Then I will try to explain what is the problem with real expansion for mixtures and what makes mixtures more complicated than just real expansions when I have just one type of particle. And what I would like to convince you of is that the step where I invert a density activity relation, that step is non-trivial because I cannot necessarily not use the standard inversion theorems where I say derivative at the origin is 0, invertible, and there you go. Then I will present one general theorem without necessarily going into proofs, and then explain why, well, maybe the theorem that we get for now from abstract machinery is not that optimal. And I will try to be a bit more concrete by looking at a model of non-overlapping rods, or if you like, a multi-species Tonks gas, and another model which is a hierarchical mixture of cubes. All right, so let's start with a recap. And let me first say what is the kind of models I have in mind. So everything I do will be in finite volume in the beginning, and then at some point I will take the limit. And I work in a finite box. Configurations are simply collections of points, gamma x1 to xn. And because I'm in a finite box, it's enough to look at collections of finitely many points. And I will call capital gamma lambda the configuration space. Now, if I absolutely want to introduce a Gibbs measure as a probability measure, maybe you don't want to, it's not absolutely necessary, I should introduce a sigma algebra. And the way this is commonly done is that you say, well, for every subset of lambda, every window of observation, if you like, you can define a counting variable or an occupation number where you simply count how many particles are there in that set. So if I write gamma being an x1 to xn, how many indices j are there for which xj is in me? These variables generate a sigma algebra on the space of configurations. And the grand canonical Gibbs measure will simply be a probability measure on that space. So then comes the standard definition of what is a grand canonical Gibbs measure. We're given a pair potential V, which may take the value infinity. And I think to uncomplicate our lives and not go into business of stability, let me just assume always that the pair potential is non-negative. We're also given a parameter, a positive parameter, which is the activity Z. And to simplify formulas, inverse temperature will always be set to 1 in this term. So there is no beta. Then there's the grand canonical partition function, which is simply 1 plus the sum over possible number of particles in the box, Z activity to the n divided by n factorial, integral over all possible positions of your particles. And then comes the Boltzmann weight, which is e to the minus total energy. And the energy is simply a sum of pairwise interactions. And a little later, I will assume that the pair potential is actually translationally invariant. So you can think here V of xi minus xj, if you like. And then the grand canonical Gibbs measure is simply a probability measure on the space of configurations, where I say the probability of a certain subset, capital A, of my configuration space is simply obtained, by this formula where I say 1 over normalization, indicator that the empty configuration is in that set, and then I sum over all possible number of particles, and here comes the expression. Another standard question for cluster expansions is, can you compute these things? Well, if the pair potential vanishes, then the exponential is just 1, and everything that is written here can be computed. The grand canonical partition function is then simply exponential of z times the volume of lambda, and expected values down here can be computed as well. In physics, you would call the corresponding model an ideal gas. Probabilists would call it a Poisson point process with intensity parameter z. And one quantity we will be mainly interested in is the average number of particles. And it is a standard trick that you can write this average number of particles as z times the z derivative of the logarithm of the partition function. And this kind of relation in probabilistic terms, you would say, well, the grand canonical partition function is a little bit like a generating function. Taking derivatives of generating functions is related to computing moments and things like this. And the idea is that, well, if z is small, then you would expect that overall the number of particles is small, and therefore the contribution from interactions should be negligible, and you might hope that there is some kind of perturbation series around the ideal gas / Poisson point process. Okay, a small parenthesis I want to make, which you can forget about completely in a minute. I will never ever use it. But I want to mention it because it is kind of nice, and I learned about it rather late. So let me use this notation with the angular brackets for the expected value with respect to the grand canonical Gibbs measure. And let me introduce the notation W of x and gamma for all the interactions between a point at x and points y in gamma. Then it's an easy exercise to check in finite volume that the grand canonical Gibbs measure satisfies this kind of structural property, where I say, well, let's say that you have a function, a test function, that depends on 2 variables. Number 1, a position in the box. Number 2, a whole configuration. And then you might be interested in observables of the form you sum over all particles in the configuration. And every particle gives a contribution which depends on the particle itself, but also on the other particles. So you could try to bring, for example, the interaction between points in some observation window with the outside world into that form. And then it so happens that this expected value you can express in a slightly different way. So you do a kind of change a variable from gamma to a gamma prime, which would be gamma with point x removed. And this turns out to be equal to the integral over the box, expected value with respect to the Gibbs measure of function, but now with a gamma union an extra point x. And then you add a factor which is activity times e to the minus interaction of the extra point with the remaining particles. This equation is sometimes called the Georgi-Nguyen or GNZ equation, after Georgi and Nguyen and Tsessin. I would say in mathematical physics, it's perhaps less well known than the DLR equations, named after Dobroshin, Lanford, and Ueltschi. This equation is very, very popular among people from stochastic geometry and point process literature, because it has something to do with characterization of the Poisson point process called the Mecke equation. But perhaps a more useful point of view to link it to mathematical physics is that this is like an elegant short version of the Kirkwood-Salzburg equation. So if you ask, what does this equation here, which is stated for the Gibbs measure, what does it mean for the vector of correlation functions? Well, you end up with a Kirkwood-Salzburg equation. Parenthesis closed. Good. Now let me first remind ourselves of how do you get to of this Maya trick, which goes back at least to the 40s, for how do you get from configuration integrals to graphs. So step number one is you write the Boltzmann weight, which is this e to the minus total energy. This is the exponential of a sum. Exponential of a sum is, of course, a product of exponentials. In the individual contributions to the product, you do a -1 + 1 trick. This leaves you with a product of 1 plus stuff, so you can expand it. And when you expand it, you have a sum over subsets of the pairs, of all possible pairs ij. And each subset contributes a product over all pairs ij contained in this set, e to the minus interaction -1. Now, each such term I can reinterpret as a graph. And this gives me that the exponential of the Boltzmann weight is simply a sum over graphs on n vertices. So this is the sum over G and Gn, where the weight of a graph is simply the product over all the edges in the graph, and each edge contributes this e to the minus vxi xj -1. And if you've never seen the corresponding pictures, so one contribution could be, if I have, let's say, n equal 3, and I pick e equal, let's say, I have two edges, 1, 2, 2, 3. And let me call this thing here fij. Then I would have a term over here where I see there's a 2, 1, 2, 2, 3. And this would come with a f12, f23, which appears in the product of 1 plus fij. All right. Good. Now, when you do that and you insert what you just got, the partition function becomes 1 plus, again, the old sum over the number of points, which I now want to think of as a number of vertices, integral lambda to the n, sum over all graphs, etc. In the language of analytic combinatorics, this would be called an exponential generating function for certain combinatorial species of weighted graphs. And I should mention that cluster expansions really enjoy a resurgence of interest from the purely combinatorial side, where people play around with these things. And a nice survey article in this direction is by Bill Ferris. Good. That's number one. Yeah.
By whom you said?
Ferris. Bill Ferris. There's a survey article called Cluster Expansions and Combinatorics, I think, around 2010, in that order of magnitude. All right. So that's step number one. And then comes step number two, which is a standard thing which appears in many different places, which is that whenever you have this kind of exponential generating function for a combinatorial object, taking the logarithm gives you the exponential generating function for the corresponding connected class of object. So if I call Cn the set of connected graphs on n vertices, then the logarithm of this thing is just given by the same series that we had before, but we only sum over connected graphs. And for now, this is only an identity of formal power series because I haven't said anything about, thank you, Daniel, because I haven't said anything about convergence. And the job of cluster expansions and my expansion is to estimate the radius of convergence of this series uniformly in the volume lambda. Good. Now, what that gives you is, so the simplest sufficient convergence condition that I'm aware of, if V is larger or equal to 0, which goes back to the 60s, so the names here would be Grunefeld and Penrose, and there's also something in the book Virial, is if the potential is non-negative, and Z times this integral, which involves 1 minus e to the minus the interaction. Notice that this is 0 if V is 0. If this is smaller than 1 over e, then the series that I just showed you is absolutely convergent. Moreover, the bounds are such that you can exchange summation and the limit lambda going to RD. So not only do you have a power series expansion of the pressure, but on top of things, if your potential is translationally invariant, you can pass to the limit and you obtain the Meyer expansion for the infinite volume pressure. And the coefficients are given by integrals involving sums over connected graphs, which is sometimes called Meyer's cluster integrals. Good. That was the Meyer expansion. Now, Virial expansion. And I should mention, I settled in the end for not even attempting to give a survey of what is going on, but I should mention that there's a lot of activity beyond this 1 over e, with many recent articles getting better, slightly better bounds. So it's not a closed topic. The Virial expansion now asks, what if you don't want to expand in powers of the activity Z, which for some people might be a slightly abstract parameter, which is difficult to observe in nature, but instead you want to expand in powers of the density rho. The density rho is average number of particles divided by volume. And now if you remember, there was the relation with the derivative of the log of the partition function. In terms of the pressure, this is Zp prime of Z. And in terms of the expansion, this is Z plus higher order terms. Well, if I look at this equation, that's something that I can invert. So I can write rho of Z equal, I can solve the equation rho of Z equal rho, write it as Z equals Z of rho plus inverted, and write the inverse function as a power series, at least in the neighborhood of the origin. And then you can compose the expansion. So you plug in the expansion of Z of rho into the expansion of P of Z, and you end up with an expansion of the P in powers of the rho, where the first order term is rho, and then come higher order terms. And this is the Virial expansion. And this expresses corrections to the ideal gas law, pressure times volume is equal to number of particles times Boltzmann constant times absolute temperature. And you can push the procedure to get quantitative bounds on the radius of convergence in the series in rho, using, for example, something called Lagrange inversion. And this you will find in an article by Leibowitz and Penrose. Moreover, the expansion coefficients, which you may or may not care about having combinatorial formulas, there are some that are available, and it is given in terms of two connected graphs. Or in physics lingo, these are Meyer's irreducible cluster integrals. And just very quickly, a graph is too connected if it is connected, and it stays connected even if you remove a point. And here, same comment as before, there are many recent articles that improve the bounds going back to Leibowitz and Penrose. And I hope the experts in the audience will forgive me for not even trying to attempt a survey at this point. Good. So that was the recap. Any questions so far? Sorry, I'm being a bit All right.
I have a question. So to connect it, is it the same as one particle irreducible graph?
No, it is not. I think one particle irreducible refers to removal of an edge.
Okay.
Whereas here I'm really referring to removal of a vertex. So this would be something which is not too connected, because if I cut out this vertex over here, I split into two connected components.
Okay, thank you.
Okay. Any other question? Good. So that was the review. And now the question is what I'm after when I say virial expansion for mixtures. And I will try to explain the problem, and to keep things concrete, I will just write down formulas for a mixture of spheres of different sizes. So the picture I would like you to have in mind is that there's a big box. And in that box, I put spheres of different sizes. Sizes can repeat, of course. There's a certain reservoir of different radii, and each sphere type comes with an activity zk. And I want you to think of picking radii essentially in such a way that the volume is proportional to little k. Though you could play, of course, with different things. And the interaction is purely hardcore. So I will put an interaction which says, well, infinite if two spheres overlap and 0 otherwise. So let me give you some formulas. So you have the set of admissible radii. For example, rk proportional to k to the 1 over d, so that the volume overall is proportional to k. Then you have activity parameters. And a little bit later, so on the next line, after that, I will choose a concrete parameter dependent version where I want you to think of this as being something of the form e to the k times mu, where mu is a chemical potential maybe of particles that make up the sphere, minus some kind of energy assigned to a sphere. And I have the hardcore interaction. Partition function, same thing as before, except that now I have to sum over multi-indices that tell me how many particles, how many spheres of a given type do I have. There's the product over activity of a k-sphere to the corresponding number of particles. Downstairs, the product of factorials. You integrate over all these things, and you put the indicator that the spheres do not overlap. Again, you define the pressure simply as 1 over volume logarithm partition function, limit as lambda goes to RT. The expansion that we're after is sum over k to leading order. If I were to neglect the indicator, again, this would be something that you could compute. Sum over k zk. And then there will be higher order terms coming from the effect of overlaps of spheres being forbidden. Or if you want, excluded volume effects. Instead of having just one density variables, I now have one for each type of sphere, given by zk times a partial derivative with respect to zk, and it will be a zk plus higher order terms. And rho k just counts the number of k spheres per unit volume. Now, let me tell you what brought me to this model. What brought me to this model was a kind of very classical but somewhat naive picture of condensation. So these are droplet models for nucleation, and I learned about them from statistical mechanics books by Terrell Hill, but it was not at this time. So think of dimension 3. Think of choosing the volume of the sphere as being equal to k. And the motivation for this is I want to think of this as a simplified model for a system of particles where actually each sphere corresponds to a group of k particles that are close to each other. It's like a droplet, and I'm making the brutal assumption that a droplet of k particles is automatically a sphere. That's very, very brutal. And then I want a parameter-dependent activity where I have e to the number of particles in the droplet, in this picture, times chemical potential, minus some energy. And the energy has a bulk term, k times E0, and then maybe a surface correction constant times k to the 2/3, and the constant should be something positive. Now, if I neglect the condition that the spheres do not overlap, so this is sometimes called the ideal mixture approximation, then, as I mentioned before, the pressure is simply the sum of the activities. Perhaps some of you remember from thermodynamics courses this law of additivity of the partial pressures in an ideal gas. And that would be simply the series sum over k e to the k times mu minus in k. And I'll come to divergence in a minute, or convergence. Another quantity of interest is the packing fraction sigma. So that would be the fraction of the volume covered by spheres. And that can be computed to be simply the derivative of the pressure with respect to the chemical potential. And then again, you have a series. Now, when you look at it, you see that the series diverges when mu is equal to E0. Just look at the concrete formula over here and apply your favorite convergence condition. At mu equal to E0, for this concrete choice of e's, this series here is finite, and it is interpreted, or it is analogous in real models. It would be something like the density of saturated vapor. And this kind of relation maybe reminds some of you of the kind of computation that you do for the ideal Bose gas, where the summation over k corresponds to summation over cycle length. And one thing I want you to notice is that at mu equals 0, when I look at this e to the k mu minus ek, well, mu equal E0 simply means that the k E0 cancels out, and I will have something coming up here, which has an e to the minus constant times k to the 2/3. These individual summands over here are interpreted as the density of k spheres just about the point where things are going to condense. And in this toy model, what happens is that over here you have sub-exponential decay of the densities. So it goes like e to the minus a power of k, and the power is smaller than 1, instead of going like e to the minus constant times k. Now, that's a model where there is no excluded volume effect taken into account. And a very naive thing you might try to do is say, well, could you somehow compute corrections to the equation for what is the density of saturated vapor? Maybe you think of some Clausius-Clapeyron equation. Some corrections that come from excluded volume effects. And if you want to do that, then you see, well, it would be nice actually, or it might be nice to have power series in the rho k that cover sub-exponential vectors of densities. So that's something to be kept in mind. That's something that I'm not able to do, but I will come back to it. Good. So now let's come back to more concrete thing. So when I want to have convergent expansions, if I'm after activity expansions, there's no problem whatsoever. I can apply, for example, one criterion from a paper by Daniel, who has a kind of continuum version of Kotetzky price conditions. There's a condition, which I don't ask you to decipher, which guarantees that I'm able to write the pressure as a power series. It converges. Therefore, also the rho k of z will be something that converges. It is zk times 1 plus higher order terms. And while this looks really nice because I have a power series look like analytic functions. So it's as differentiable as it gets. And I can compute the derivative of the vector of rows with respect to the vector of z's at z equals 0. And if you just look at this thing, you'll see, well, you just end up with the identity matrix. A derivative that is an identity matrix, well, identity matrix looks invertible. So it looks like we're completely set to apply some inverse function theorem. And when you have only finitely many types of spheres, this is what you can do, and this is what has been done in the past. And I want to convince you in a minute that there's a problem with this when you have a vector of infinitely many row Ks. Well, that can be a problem. Before I try to convince you of that, I want to point out one other thing. So I told you that I'm not asking you to decipher this equation. But I do want you to notice that it comes as a sum over activities, and then each activity has an exponential, and in the exponential there is the size of the sphere. So I want you to think of this sufficient convergence condition as some kind of weighted L1 norm of the vector of activities is small. And the weights in the L1 norm have exponentials of the volumes of the object. And for this to be small, you see, you need activities that, to be even finite, you need activities that go to 0. So ZL would need to go to 0 as e to the minus some constant times the volume of the sphere. Okay. So now let me give you a toy example, which you may or may not find convincing, but that's the kind of thing that I'm after, where I say, well, what kind of thing could go wrong if you're after vectors of infinitely many z's and rows? So let me look at a map, and since I'm after functions of after power series and analytic stuff, let me just take vectors of complex entries. So sequences of complex numbers to sequences of complex numbers, where I map z's to rows. Row 1 is equal to z1. And for k larger than 2, row k is simply zk times e to the minus kz1. This example is not entirely arbitrary. It's really motivated by formulas that you will see a little bit later about non-overlapping rods on a line or hierarchical mixture of cubes. Good. Now, this is really concrete. So this, I can invert it as a map from Cn to Cn by hand, because this is just Z1 is equal to row 1. And then Zk is equal to row k times e to the k row 1. But let's pretend we didn't notice that we can invert this by hand, and let's see if I didn't notice, what would have happened if I tried to apply some kind of inverse function theorem. Well, because I have vectors, it's natural to try to work simply in Banach spaces. And because of the shape of this relation, and also because of the sufficient convergence condition that I just showed you on the previous slide, it's natural to work with Banach spaces where you just ask that some weighted L1 norm is finite. And I'm keeping the freedom to choose the parameter in the exponential and the weights for the weighted L1 norm. So I have several of them. And then what you would want to have is somehow choices of initial Banach space and target Banach space. And let's say I give myself the freedom to have initial and target different, such that your function would be, at least when restricted to some neighborhood u of the origin, you would want this thing to be Fréchet differentiable, I mean, just differentiable in the norm sense. And you would also want the derivative, to the very least at the origin, to be a bijective map, invertible with bounded inverse. because that's what I want for inverse function theorems between Banach spaces. But now you see there's a problem, because if I look at this relation rho k equals zk e to the minus k z1, as soon as z1 is different from 0, you see the exponential tails of rho k and zk, they're not exactly the same. And what's worse, if I really want open neighborhoods of 0, I don't know what is the sign of the z1, so I don't know, depending on z1 positive or negative, who grows faster or slower. But anyway, what this relation tells me is that I cannot choose A equal B. It won't work. But if A is different from B, and if I come back to this observation that the Jacobian is the identity matrix, it's actually not an identity operator. The best you can hope for is that it's an embedding from one Banach space into another one, and the norms in the Banach spaces are not equivalent, and the inverse, I mean, it's not surjective, or the inverse is not bounded. And that was the thing that caused us a little bit of trouble in the paper with Daniel a long time ago, and then in a more recent paper. So there is no way to choose A and B to make it work. And a remark that people from analysis sometimes make to me is that, well, actually there is, I mean, here I have a scale of Banach spaces, which might remind you of scales of Sobolev spaces. And there is a theory to deal with this kind of things, and this is Nash-Moser inversion. You could do that. We try to clarify what happens if you try to apply this framework, but you don't have to. You can do something else. So I hope I convinced you that at least the naive thing you can try to do does not work. And if anyone has another idea of how this should be done, with more expertise in analysis, I'd be very happy to learn about it. So let me explain that nevertheless, there's a theorem that you get, and that's the following. And this one is from a paper with Tobias Kuna and Dimitrios Tsagkarogiannis, and it's in a way a continuation of an earlier paper with also Stephen Tate and Daniel Ueltschi. We have a theorem that is much more general than mixtures of hard spheres, but let me stay in that concrete setup. The condition says the following. Suppose you can find a number A such that, again, you have this kind of weighted L1 condition. And it's exactly the same that we had earlier, except that now I'm putting a 2A up here. It's the only difference with what we had earlier. Then I know that I can invert. More precisely, I can define a vector of z's by a concrete formula like this. Okay, maybe it looks less concrete to you than it does to me. You can define a vector of z's by defining zl to be rho l times a correction. The correction I write as an exponential of a power series. The power series has a sum over n, which is like number of spheres that can overlap. And here a sum over possible assignments of sphere types. Then comes an integrand. And the integrand, I don't want to give a formula, but it is again given as a sum over two connected graphs on n+1 vertices. And then there's a product of row-case. So there is a formula. Under this sufficient convergence condition, we do know that it is absolutely convergent. Actually, we have a bound. And for this z, I know that the density at this z is equal to the given vector of rows. Good. And this kind of formula, I mean, the fact that the inversion should have this form with the two connected graphs, that's not new at all. So these formulas you find in the physical chemistry literature from the 60s and 70s, or maybe, yeah, I think that's the references I'm aware of. Our main point is about convergence. Good. And if you don't want to read the formulas, just keep in mind the inversion can be done despite this inverse function theorem problem. And the way we prove it, I won't explain it, but I at least want to mention a keyword, is that we use a formula for the inverse power series, which expresses an inverse power series as a sum over trees. And this seems to be something that comes up in many different shapes in a lot of different places. So to my surprise, I ended up opening a paper from algebraic geometry at some point, which had these formulas. So this we do, we have a concrete formulas in terms of trees, instead of using an analytic function, inverse function theorem. It's a bit different from what we did in an older paper. What we did there is that we used multivariate Lagrange good inversion, but again, I won't say what it is, just another keyword. Any questions on the statement of the theorem? Okay. So let me say again, this condition over here.
Or perhaps a quick question, if I may. So for this model from a hill where the energy grows like k to the 2/3, would it work? Because the rho k might not decay fast enough with respect to k.
So yes, I mean, I think that's exactly what I wanted to say. It's still not good enough to have something that has sub-exponential decay, right? So that's the part where I say I'm actually not that happy yet about the theorem. I would like to have something better, but I'm completely unable.
Sure.
Yes, exactly.
And so do you assume the dimension, I mean, is it an abstract theorem, or do you assume that dimension is 3, etc.? It's
an abstract theorem, and it generalizes to systems where you don't have hardcore interaction. You can have attractive interactions, you can have soft interactions, and you can even have not a countable reservoir of different radii, but really a continuum space of object types, if you like.
And this combinatorial formula for inverse with trees, is it a kind of a classic formula? I mean, does it have a name, or?
So it's related to different formulas with different names. One is the Bass-Connell-Wright formula. So this would be typically a name that rings a bell within the community of more closer to algebraic geometry, I think, where people are interested in the Jacobian conjecture. I don't quite remember what that is. When we explained this to somebody else, we were pointed out to the fact that this is also very closely related to something in statistical mechanics, which is the Galois-Nicolo trees. It's supposed to be an O. So these come up in two places. One would be renormalization, I think, and the other would be perturbation series as something called the Lindstedt series in CAM theory and dynamic of the systems. So these would be two keywords that are very much related.
Thank you.
Okay. So much for the abstract theorem. I mean, semi-abstract because hard spheres, I wrote it down for hard spheres. Now, as we just noticed, that's still not quite what we want to. So the theorem still imposes this kind of decay. The question is, can I get rid of it in order to have something like surface of the sphere instead of volume of the sphere? In general, I don't know. And let me just mention two examples where you can compute stuff explicitly. Also, perhaps in order to end up on a slightly lighter note. So the first example is non-overlapping rods on a line. I also call it a Tonska. So you just have a line and you have rods of different length. And the rods lengths are just denoted by LK. That's a very classical model. And what you can prove here is that you can compute the pressure activity expansion explicitly. And it turns out that for this model, you have an if and only if convergence condition for the activity expansion, which is this condition over here. And let me emphasize, it's an if and only if. So you confirm that for this model, you really need the exponential decay of the activities in the rod length. On the other hand, you can also compute the pressure and activity as a function of the density. And for the single species case, this is really old formulas. I think the paper by Thomas is maybe from the 30s. So the pressure as a function of the densities is given by the sum of the rho k's divided by 1 minus the fraction of length covered by rods. And I hope that some of you recognize the van der Waals equation. Except now you have a multi-species van der Waals equation. You can also invert the density activity relation by hand. And it turns out to be zk of rho is equal to rho k divided by 1 minus packing fraction. And then comes an exponential rod length density 1 minus packing fraction.
Excuse me, I thought the van der Waals equation was relevant for 3 dimensions, and this is 1 dimensional.
I think you can also do it in 1 dimension. I mean, I guess physically you'd be more interested in 3 dimensions, but the nice thing about rods in 1 dimension is that it's actually correct. Okay, so now this tells you 2 things, these 2 explicit formulas. Number 1 is that if I now, I mean, this is an explicit formula where I don't even have to write down power series, but if I absolutely wanted to do power series, you see, all I have to do is to expand this 1 over 1 minus, and it's absolutely convergent if and only if I have this condition over here. And so indeed, you have one example where you see there is no exponential decay of the density vector needed. There's another thing which gives you a little bit of a hint of what is a mechanism why one expansion might be better than the other. You see, the zk is like a density rho k times an exponential. So the activity is really exponentially larger than the density. And this is actually not a feature just of this example. This is something that you can prove more generally. And this is what gives hope that what I would like to have might be correct, but certainly no proof. That was one example. Number 2 is another toy example where I look, so now I'm moving away from RD, I'm placing myself on ZD, and I look at a hierarchical mixture of cubes. So here you see a schematic. I didn't do the picture myself, a friend did it for me. And a configuration is simply a collection of non-overlapping hypercubes in ZD. My cubes have side length 2 to the j, where j is an n0. And the admissible locations of endpoints of cubes is such that, so a cube of side length 2 to the j have all coordinates in the upper right corner, a multiple of 2 to the j. And the effect of this is that if you take any 2 admissible cubes of different shapes, if they overlap, then necessarily one is contained in the other. So that's sometimes called, or very often called, hierarchical geometry. I think one early reference where the word is used is a paper by Dyson on the hierarchical easing model. And it's a frequent starting point in a certain type of analysis of renormalization group theory. And I learned about this from lecture notes by David Bridges. And actually the paper that I'm just going to present one result of came out from active reading of those lecture notes by David Bridges. So for this type of model, you can say the following. I mean, a lot more, but that's one other thing. Let me use the letter capital Bj for a representative cube of side length 2 to the j. And let me introduce an effective activity, Z hat j, which is the activity of a j cube divided by the partition function for that cube. So think of some effective parameter that takes partially excluded volume effects into account, namely here the fact that once I place a cube of side length 2 to the j, I cannot place any smaller cube into that same region. And I suppose that your parameters are such that the effective activities are summable. Then the pressure is given by this explicit formula, which shares some features with van der Waals. I mean, you see there's again a rho divided by 1 minus some area that is covered. The fact that the logarithm appears and I have a logarithm of 1 plus something, this is because I'm placing myself on a lattice and not on the continuum. And this funny looking 1 over bj in front comes because I don't have full translational invariance, right? I mean, when I have a cube of a certain side length, I cannot just translate it by the lattice width. I have to translate it by 2 to the j. And this is why the formula looks a little bit different from what you might expect if you're used to polymer partition functions. All right. So again, I have a kind of formula over here. And again, you should observe, if I wanted to, so whatever I need to make the row power series expansion of this kind converge will not involve exponential decay of the row case. And again, one can invert the density activity relation by hand, and the Zj is now equal to a rho j times an exponential in the volume of the cube times a pressure associated with some smaller volume, which I can also express in terms of the row case, but feel free to ignore this last formula. Just notice that again, Zj and rho j, there's an exponential in the volume up here. And this is what motivated a little bit my choice of a toy model, where I wanted to explain what kind of problem could happen. And here again, you see the density expansion seems to be nicely behaved in the sense that for this model, there is no conditional exponential decay. Good. And that's what I wanted to say. So to summarize, I hope I convinced you that inverting the density activity relation for mixtures of objects with unbounded size is actually non-trivial. It's not just your standard inverse function theorem. But it can be done. And I hope to say more about the trees part, hopefully in presence in Geneva in August. So we did prove a sufficient convergence condition that works well when the activities of large objects, I want the densities over here. So, because for the activities, that's not new, this we knew. So it works well when the densities of large objects are exponentially small in the object size. I want to mention again, though I didn't type it down, that the theorem actually also extends to attractive interactions beyond hardcore. And you can do stuff where instead of having spheres of different sizes, maybe you want to have density profiles, rho of x, that depends on some position. So there's a link with density functions. Or you could say, well, what if your set of possible sphere radii is not discrete but continuous, etc., etc. So it's much broader than that, but I didn't want to bombard you with too much notation. And then, well, the theorem is not quite satisfactory because the examples, the two examples that I just showed you, they suggest, perhaps wrongly, I mean, I don't know, that there should be some better condition that does not impose exponential decay. And in order to get there, I think there's still a lot of work to be done. And with that, thank you for your attention.
Thank you very much, Sabine, for this great talk. Are there questions? So I see people clapping. I wonder whether people are raising hands also. Yeah.
May I have a question?
Sure.
So can you go back to this model with hypercubes?
Mm-hmm.
So it depends on the dimension d. So in the formulas that you gave, I did not see the dimension.
Those formulas do not depend on the dimension. The only way the dimension enters is through the B.
And so the B is the volume, is the d-dimensional volume of the cube. Of the hypercube.
Yes.
So can it be formulated in a different way which does not see the dimension at all, or?
Oh, I don't think so. I think that the volume of the hypercube is really an input that I need.
I mean, usually such models depend heavily on the dimension, and this one does not, it seems.
Yeah. So I don't know if this helps, but what some people suggested to me is that I should view this rather as some kind of tree-like model, where you say there's a kind of branching structure, which is whenever I have a cube, a hypercube, it prevents someone has these 2 to the d children. And so it's like asking, how does your model depend on the degree of the tree?
I see, okay.
And it turns out that in that case, the formulas are pretty general.
Thank you. Other questions?
I mean, both these examples are hierarchical.
The cube, yes. The one-dimensional example, no.
Oh, okay. Routes is not okay. Yeah.
Yes, routes is not hierarchical. It's funny that still you end up with equations that share some degree of similarity. So there's something I don't really understand what is happening,
but the whole method, this Galavotti-Nicola and whatever method, applies to all kinds of models. I mean, applies to real sort of real statistical physics models.
Yes. So here, these what I showed you, these 2 concrete examples, I don't use Galavotti-Nicola trees or anything like that. This is really doing all the computations by hand. The question is somehow, what's the next step? And the suggestion would be to try to say, well, perhaps what the hierarchical cube tell you is that you should try to combine cluster expansion and some renormalization approach. So where you integrate out the smallest cubes bit by bit, you move up the cube sizes, and there should be something from these Galavotti-Nicola trees, but I don't know these things well enough yet.
Yeah, because your general result with Tsagkarogiannis and Kuna is, I mean, applies so much more generally. So the advantage of a hierarchical model is that you can do exact calculations and compare with a general model. And do you expect a phenomenon like condensation? I mean, some kind of Bose-Einstein condensation, because you have these objects of various sizes. So there could be a phase transition where you get very large objects appearing.
So for the hard spheres, I would expect that I don't know. And both for the rods on the line and for the hierarchical mixture of cubes, you can play around a little bit by choosing your activity parameters. And depending on your choice of activity parameters, you can produce models with phase transition where you go to large cubes. And you can produce models with first order phase transitions or with continuous phase transitions. So it's also a nice feature of the examples is that you can also go to this phase transition question, which I cannot answer for hard spheres.
Thanks. Other questions? So perhaps a last question. So the convergence of a Virial expansion is somehow easier than the cluster expansion. I'm not talking mathematically, but
for repulsive interactions, that's what I would expect, not for attractive.
That's right. Yes.
Mm-hmm.
So yes. So there are examples where one converges, but not the other.
Yes.
Yeah.
Yes. But the mechanism really is, or one feature is, you see it here well for the tongue scales, is that the ZK is typically exponentially larger than the rho K.
Mm-hmm.
And in physics, I mean, here this comes out from some explicit computation that the way one should really think about this, which I haven't mentioned, is that if you want to know what is rho K as a function of the activity for, let's say, back to the hard spheres, it is really rho K is equal to ZK times the probability with respect to the Gibbs measure that if you look at your K sphere, there is no other sphere intersecting it. This is a number which is smaller than 1, and the probability that no sphere whatsoever intersects this thing over here, it's kinds of cavity functions, and I think this kind of relation goes under all kinds of different names in the physical chemistry literature. It's not hard to believe that this is something that is exponentially small if the volume that you ask to be empty is large. So the rho K is smaller for hardcore systems, exponentially smaller than the ZK in this volume. And that's really something physical. It's not something that comes out of funny computations.
Yeah, thanks. Other questions? Peter Wildemann?
Yes.
Yes.
Hello. So maybe this question might be stupid, but so can you apply these kinds of results to get something about like semantic type loop soups? Do you know what I mean? Like I have loops of arbitrary length and interacting repulsively.
Well, in theory, it looks like it, but I don't know if the convergence conditions give anything good. I've never tried.
Like I would expect probably that if you are beta is less than 1, then your activity converges is exponentially decaying.
Yes, I mean, I would suspect that if your ZKs go really, really small with K, there should be a chance of getting something. But I don't know if this is the regime of ZKs that you would be interested in, whatever concrete model you work on. That's not clear to me. I think that's really a computation to be done there.
Thank you.
Thank you. Other questions? No other questions. So thank you very much, Sabine. So we can stop the recording.